Hello chemistry students, this is Dr. Tullis. In this section we are going to look at a voltaic cell and identify the half reactions occurring at the anode and at the cathode, the polarity of the electrodes, the direction of electron flow in the external circuit, and the direction of ion flow in the salt bridge. Devices that use chemical reactions to produce an electric current are called voltaic cells or galvanic cells. All voltaic cells work in the same general way. They use product-favored redox reactions, and the electrons from the species being oxidized, the reducing agent, are transferred through an electric circuit to the species being reduced. A voltaic cell converts chemical energy into electrical energy. The opposite process, the use of electrical to affect a chemical change, occurs in electrolysis. An example is the electrolysis of water, in which electrical energy is used to split water into hydrogen and oxygen. Electrolysis is also used to electroplate one metal onto another, to obtain aluminum from its common ore, and to prepare important chemicals such as chlorine. The reaction of copper metal and silver ions can be used as the basis of a voltaic cell. By placing the components of the two half reactions in separate compartments, referred to as half cells, electrons can only be transferred from copper metal to silver ions through an external circuit, and useful work can potentially be done. Let's look at some key components when it comes to some simple voltaic cells. We always have a salt bridge. In the case of this reaction, it's sodium nitrate. And we can see here's our salt bridge with sodium ions and nitrate ions. The anions migrate towards the anode. The cations migrate towards the cathode. How do we figure out which one's which? Well, the anode is where the oxidation happens. You can remember this because anode is a vowel, oxidation is a vowel. The cathode is where reduction occurs. Both begin with a consonant. Electrons flow from the anode to the cathode. This is the electric current. The anode produces the electrons, and the cathode is the positive electrode. If we look back at this voltaic cell, we have copper plus silver ions producing copper ions and solid silver. If I assigned oxidation numbers, copper would be 0. Copper plus 2 obviously is where oxidation is happening, going from 0 to plus 2. Oxidation is losing electrons and becoming more positive. So because that's oxidation, copper will be at the anode. The anode is always on the left. Silver, going from plus 1 to 0, has been reduced. Because it's undergoing reduction, it is the cathode. And the cathode is on the right. We said electrons flow from the anode to the cathode. And you can see here that the electron flow is from the copper anode going to the right to the silver cathode. The electrodes are connected by wires to that voltmeter. In an alternative setup, the connections might be to a light bulb or other device that uses electricity. Electrons are produced by oxidation of copper, and the copper plus 2 ions enter the solution. The electrons traverse the external circuit right up here to the silver electrode, where they reduce the silver plus ions to silver metal. A salt bridge is always required in a voltaic cell because there must be a complete circuit of charges for current to flow. If the salt bridge was removed, the electrode reactions would cease. And again, electrons move from the anode, which is the site of oxidation, through that external circuit to the cathode, which is the site of reduction. Charge balance in each half cell is achieved by migration of ions through the salt bridge. And we see here that when we look at the cathode and the anode, or the reduction and the oxidation half reactions, there are 2 electrons and 2 electrons on both sides, which show us those electrons that are migrating through the salt bridge. Negative ions move from the reduction half cell to the oxidation half cell, and positive ions move in the opposite direction. We can see here the negative ions are moving from the cathode or the reduction to the oxidation, and the positive ions are going from the oxidation to the reduction, so going to the right. To obtain a current that can do work, the oxidizing and reducing agents are separated so that electron transfer occurs via that external wire. This is accomplished in a galvanic or a voltaic cell, and a group of such cells is called a battery. Each of those two compartments is called a half cell. Typically, electrodes are made of conducting materials like platinum and graphite. These do not gain or lose mass during reactions, and they serve as a surface for electron exchange. Let's describe how to set up a voltaic cell to generate an electric current using this reaction. Which electrode is the anode, which is the cathode, in which direction do electrons flow in the external circuit, in which direction do the positive and negative ions flow in the salt bridge, and let's write equations for the half reactions that occur at each electrode. First, let's figure out each half reaction. I'm going to look at iron, give it an oxidation number of 0, same with copper, 0. 0 to plus 2, iron will be oxidized, and copper plus 2 to 0 is being reduced. So my half reaction for iron will be FeS to Fe2 plus, and because of that 2 plus, I'm going to need 2 electrons on the right. And for the reduction, we've got our copper plus 2 to copper solid, so that means I'm going to need 2 electrons on the left. Remember, oxidation starts with a vowel, so this is going to be the site of my anode. Reduction is a consonant, that will be the site of the cathode. The anode is on the left, so I would have the iron in this half cell. On the right, I would have the copper cathode. In the salt bridge, we could have the same NaNO3 as the last example. They used KNO3 in this case. It doesn't matter, but we do want a unreactive salt in that salt bridge. Some common ones are sodium chloride, potassium chloride, sodium nitrate, potassium nitrate. They are all salts and weak electrolytes. And then we have this voltmeter with our external circuit, and electrons are flowing from the iron anode to the copper cathode. And in our salt bridge, the negative ions are going toward the iron and the iron 2 half cell, which actually goes right in line with that whole circuit. The negatives are going to the left, and our positives are going to the right in the opposite direction. What about this example? Pause it and see how you would set up this voltaic cell using those half reactions. Well, we are told that our oxidation half is the nickel plus 2, so that's where our anode will be. And the silver plus to silver solid is our reduction half reaction, so that will be our cathode, will be our silver metal. With our silver electrode at the cathode, we need to have a solution that contains silver plus ions. And with the nickel electrode, that's the anode, we need a solution that contains nickel plus 2 ions. And we connect the 2 half cells with the salt bridge. When the electrodes are connected through that external circuit, electrons will flow from the anode, which is the nickel, to the cathode, which is the silver. Our overall reaction after we balanced it would be this guy. The negative ions are going to flow from the silver to the nickel, and the positive ions will flow in the opposite direction. In the half cells that we've looked at so far, the metal that's used as an electrode, either the anode or the cathode, is also a reactant or a product in the redox reaction. But not all half reactions involve a metal as a reactant or product. With the exception of carbon in the form of graphite, nonmetals are unsuitable as electrode materials because they don't conduct electricity. It's not possible to make an electrode from a gas, a liquid, except mercury, or a solution. Ionic solids do not make satisfactory electrodes because the ions are locked tightly in a crystal lattice and those materials don't conduct electricity. In situations where reactants and products cannot serve as the electrode material, an inert or a chemically unreactive electrode must be used. These electrodes are made of materials that conduct an electric current but are neither oxidized nor reduced in that cell. Here's an example where I have iron 3+. It's being reduced to iron 2+, so that's my reduction half reaction. H2 gas, which has an oxidation number of 0, is being oxidized to H+. So that's my oxidation half reaction. Therefore, my iron, since it's being reduced, will be the cathode. I can have iron metal as my cathode. But at the anode, I can't have hydrogen gas as my anode. In this case, graphite is a commonly used electrode material. It's a conductor of electricity, it's inexpensive, and is not readily oxidized under the conditions encountered in most cells. Mercury is used in a certain type of cell. Platinum and gold are also commonly used in the lab because both are chemically inert under most circumstances, but they are generally too costly for commercial cells. Here we have the hydrogen electrode, and it's particularly important in the field of electrochemistry because it's used as a reference in assigning cell voltages. The electrode material is platinum, chosen because hydrogen adsorbs on the metal surface. In this half cell's operation, hydrogen is bubbled over the electrode, and adsorption on the large surface area maximizes the contact of the gas and the electrode. Here is a voltaic cell involving the reduction of Fe3+ to Fe2+ with hydrogen gas. And in this cell, the hydrogen electrode is the anode, and the iron-containing compartment is the cathode. And you can see that hydrogen anode, and in here we have that chemically inert platinum electrode. This cell produces 0.77 volts. Let's look at some electrochemical cell notations. Chemists use a shorthand notation to simplify cell descriptions. For example, the cell involving the reduction of silver ion with copper metal is written as this. By convention, on the left, we write the anode and the information with respect to the solution with which it is in contact. A single vertical line indicates a phase boundary, and the double vertical lines indicate the salt bridge. So this shows me that on the left side of my cell, I have my anode. On the right side of the cell is the cathode, which, remember, back here on the left side of my cell is my anode, and on the right side is the cathode. Going back to this reaction, remember that my copper anode, because it's been oxidized, it went from solid copper to copper plus 2. Solid copper to copper plus 2. So when I write it in this notation, I write the solid copper, single line, copper plus 2. You also include the phases, solid copper, and this is aqueous solution, and we do include its concentration. This is a 1.0 molar solution. My cathode is where reduction has happened, and that was when I had Ag plus ions reduced to Ag silver plus 1 to a 0 was reduction. So I show my plus first. It's an aqueous solution. It was a 1 molar concentration, single line, solid silver. For this next one, the cell that's using hydrogen gas to reduce iron 3 ions is written like this. We have our platinum electrode, which we have here on the left. Then we show our hydrogen, which went from hydrogen gas 0 to plus 1. It's the anode. It's been oxidized. And then we have our salt bridge. And then we show that our Fe3+ was reduced to Fe2+. And again, we show that chemically inert platinum electrode on the far right. Here's another example showing zinc plus copper 2+, reacting to form zinc 2+ and copper. You first need to figure out who goes on the left. So we need to assign oxidation numbers and figure out our two half reactions. Zinc going from 0 to 2+ has been oxidized. Therefore, it is the anode. That goes on the left. Zinc solid, single line, zinc 2+, then our salt bridge, and then copper 2+ reducing to copper 0, so copper 2+ to copper solid. See if you can determine the oxidation reduction half reactions and the overall chemical equation for this electrochemical cell. Once I see platinum, I know that that must be the electrode. I'm going to look at H2, has an oxidation number of 0, and H+, so going from 0 to plus would be my oxidation, or the anode. So I would say H2 to H+, which means I would have an electron on the right. But then I go back and I go, oh, I have two H's on the left, so I would need two H+, which then means I need two electrons. And then when I look over here, I've got bromide in aqueous solution, silver bromide and silver. Let's look at these oxidation numbers. I have a negative. In silver bromide, I have a +1 and a -1. And then silver solid is 0. So the bromide is negative and negative. That didn't change. But silver went from +1 to 0. So that must be reduced. This is my oxidation. My reduction half would be AgBr, reducing to Ag solid, and our bromide ions. The bromide didn't change, but notice on the right here I have 1 negative, so I would need 1 electron on the left. Notice I have 2 electrons on the right here, so I would need 2 electrons on the left, which means I need to multiply everything by 2. So 2 electrons plus 2 silver bromides, giving me 2 silver solids plus 2 bromide ions. My 2 electrons and 2 electrons will cancel out, and if I bring everything else down, I should have an overall chemical equation of this. Pause here and look at this overall chemical reaction. Use cell notation to describe the electrochemical cell. How did you do?